In this lecture video, we're going to learn how to test a claim about a standard deviation. Let's start by reviewing the steps of hypothesis testing. First, we need to list out the null and alternative hypotheses. Next, we need to calculate the test statistic. Third, we need to find the p-value or critical value. And fourth, we need to determine and state the conclusion. It's also important that we understand correct notation. Lowercase n is the sample size. Lowercase s is the sample standard deviation. Sigma is the population standard deviation. S squared is the sample variance. And sigma squared is the population variance. We will not be using our calculators to conduct this hypothesis test, so it's important that you do understand how to calculate the test statistic by hand. The test statistic is a chi-squared value, and when you calculate your test statistic, make sure you round to 3 decimal places, as you'll see in the chi-squared distribution. When we're testing a claim regarding the standard deviation or variance, the p-value method, critical value method, and confidence interval method produce the same exact results. For example, if we're constructing a confidence interval with a confidence level of 95%, this is equivalent to conducting a hypothesis test with a significance level equal to 0.05. They will both produce the same results. Let's take a look at an example. It is claimed that post-1983 pennies have weights with a standard deviation less than 0.023 grams. A simple random sample of 35 pre-1983 pennies has a standard deviation of 0.03910 grams. Use a 0.05 significance level to test the claim that pre-1983 pennies have weights with a standard deviation greater than 0.023 grams. Once we've done this, we'll be able to determine if it appears that weights of pre-1983 pennies vary more than those of post-1983 pennies. Notice that this example refers to 2 different populations, and it's important that we do not get them confused. First, we have this statement about post-1983 pennies. Those have a standard deviation less than 0.023 grams. But our hypothesis test has everything to do with pre-1983 pennies. We will compare the two when we're done. The claim is that pre-1983 pennies have weights with a standard deviation that's greater than the standard deviation of post-1983 pennies, 0.023 grams. Let's start out by listing what we know. We are given some sample data. We have a sample of size 35 with a sample standard deviation of 0.03910 grams. The claim is that pre-1983 pennies have weights with a standard deviation greater than 0.023. And writing this symbolically, the claim is that the population's standard deviation is greater than 0.023 grams. Now we are ready to determine the null hypothesis and alternative hypothesis. Step 1 in hypothesis testing is to determine that null hypothesis, H0. That's the statement of equality, that the population standard deviation is equal to 0.023, that there isn't a significant difference. The alternative hypothesis in this case will match up with our claim that the population standard deviation is greater than 0.023. This also clues us in that this will be a right-tailed test. And speaking of, let's start our picture. Recall that the chi-square distribution is skewed to the right, and that values can be 0 or positive, but not negative. We are conducting a right-tailed test with alpha equal to 0.05. This leaves an area of 0.95 to the left of the critical value. The second step in our hypothesis test is to calculate the test statistic. And in this case, we have chi-squared is equal to n-1 times s squared divided by sigma squared. We have a sample of size 35, so n-1 is equal to 34. We have a sample standard deviation of 0.03910, and the population standard deviation found in the null hypothesis is 0.023. Rounding to 3 decimal places, this gives us a test statistic, chi-squared, equal to 98.260. Now we have 2 options for step 3. We can go the critical value method or the p-value method. I'll show you both. First, for the p-value method, we need the area to the right of our test statistic. In order to do this, we're going to need our chi-squared distribution table. The chi-squared distribution table has degrees of freedom down the left column. Since our sample is size 35, we technically want our degrees of freedom to be n-1 or 34. But scrolling down, notice that in this version of the table, our values jump from 30 to 40. 34 is pretty in the middle of 30 and 40, but we will round down to be more on the conservative side, so we choose a degrees of freedom of 30. Now we need to look down this row and find the chi-squared value that's as close to our test statistic as possible. These are listed from least to greatest, and our test statistic is larger than any of them present here. It's somewhere out here off to the right. Looking at the top of the table, we can see what this means. The chi-squared distribution table gives us the area to the right of the chi-squared value. If we are farther to the right than any of these values, that means that the right area corresponding to our test statistic is smaller than the smallest value listed. It's smaller than 0.005. Let's take this back to the example. Looking at our chi-squared distribution table, we used a degrees of freedom equal to 30 and our test statistic, chi-squared, equal to 98.260. This value was off the chart, which means that it has a right area less than the smallest value listed, or less than 0.005. That's our p-value. So when we compare our p-value to alpha, we have a p-value that's less than 0.005 and alpha equal to 0.05. Clearly the p-value is smaller than alpha, so our conclusion is to reject the null. Adding this to our picture would look something like this. Since our p-value is smaller than alpha, our test statistic must be really far out to the right. The p-value is less than 0.005. Now let's back up and try this again using the critical value method. With the critical value method, instead of worrying about the p-value or the area associated with the test statistic, we're instead going to look for the critical value. That's the value associated with this right tail that has area alpha. That is, we're looking for the chi-squared value that has a right area of 0.05. Let's head over to our chi-squared distribution table. Once again, our sample size is 35, which means our degrees of freedom is 34. And since that's not an option on our table, we'll go with the closest value and rounding down to be conservative and choose degrees of freedom 30. The critical value that we are interested in has a right area of 0.05, and we can find that value across the first row. Where these two values meet up, we have our critical value, 43.773. Let's take that back to the example. Using degrees of freedom equal to 30 and a right area of 0.05, we found our critical value, chi-squared, to be 43.773. And adding that to our picture, we have 43.773 associated with alpha. Compare that to the location of our test statistic. Our test statistic is 98.260. Clearly, that's much larger than the critical value, so it must be farther to the right or more extreme than the critical value. That puts our test statistic in the rejection region, which causes us to reject the null. With examples like these, I find that the critical value method is a little more straightforward. Using common values for alpha, it's a little more clear where we land in the chi-squared distribution table. But again, both methods are equivalent. Since we've rejected the null, that would mean that there is sufficient evidence to support the claim. We could state something like this. There's sufficient evidence to support the claim that pre-1983 pennies have weights with standard deviation greater than 0.023 grams. So, does it appear that the weights of pre-1983 pennies vary more than those post-1983? Yes. If the standard deviation is greater for pre-1983 pennies, that would mean that their weights are more spread out or vary more than those pennies made after 1983. Let's take a look at another example. Listed below are the speeds in miles per hour measured from southbound traffic on I-280 near Cupertino, California. This simple random sample was obtained at 3:30 p.m. on a weekday. Use a zero point 0.05 significance level to test the claim of the highway engineer that the standard deviation of speeds is equal to 5 miles an hour. Let's start out by taking a look at our sample data. This time, instead of summary statistics, we are given the raw data values. We have a sample size of 12 because there's 12 data items, and we can find the sample standard deviation using our calculators. We can put these individual values into a list and then run one var stats, or one variable statistics, to find the sample standard deviation. Rounding to one more decimal place than what's given in these data values, we find that the sample standard deviation is 4.1. You should definitely pause this video here, put these values into your list, and make sure that you know how to find the sample standard deviation. Now let's take a look at the claim. The claim is that the standard deviation of speeds is equal to 5 miles per hour. Writing this symbolically, we would have that the population standard deviation is equal to 5. Working on our null and alternative hypotheses, our null hypothesis is a statement of equality, which means at this time the null hypothesis that sigma is equal to 5 corresponds with the claim, and the alternative hypothesis will be the statement that sigma is not equal to 5, that the standard deviation is not 5 miles per hour. Because of this, we know that we're going to have a two-tailed test, and we're asked to use 0.05 as our significance level. So alpha is equal to 0.05. Let's start our picture. We have a chi-squared curve that's skewed to the right, and a two-tailed test with alpha split into the two tails. We have alpha over 2, or 0.025 in each tail. That leaves an area of 0.95 left in the middle. Let's calculate our test statistic. That's chi-squared equal to n minus 1 times s squared divided by sigma squared. Substituting our values, we have a sample size of 12, so n minus 1 is 11. We have a sample standard deviation of 4.1 and a population standard deviation found in the null hypothesis of 5. Putting this into our calculator and using really good order of operations, we find that our test statistic, chi-squared, is equal to 7.396. If you would like to use the p-value method, you'll need to find the area in the tail associated with this value for chi-squared. I'm going to run through the critical value method again. In this case, we need two critical values because this is a two-tailed test. The left critical value will have a right area of 0.975, and the right critical value will have a right area of 0.025. And we'll make sure to use degrees of freedom equal to n minus 1. In this case, that's 12 minus 1, or 11. Let's head over to our chi-squared distribution table. This time, our degrees of freedom is one of the options on the table, 11. Now we need to find the critical values that are associated with a right area of 0.975 and 0.025. Looking across the row with degrees of freedom 11, we find our two critical values. They are 3.816 and 21.920. Let's take those back to the example. We have a left critical value equal to 3.816 and a right critical value equal to 21.920. Now let's compare our test statistic to these critical values. Our test statistic is 7.396, which is somewhere between the critical values and not in the rejection region. So our conclusion in this case is that we fail to reject the null. And in failing to reject the null, we have failed to reject the claim. So our concluding statement might sound something like this. There is not enough evidence to reject the claim that the standard deviation of highway speeds is 5 miles per hour. That's about as strong of a statement that we can make, but the implications of this conclusion is that it's quite possible that the standard deviation of highway speeds is 5 miles an hour. That concludes this lecture video on how to test a claim about a standard deviation.